Hey there, chemists, welcome back. So we've been talking about equilibrium and reversible processes, and today we're going to look at what's called Le Chatelier's principle, which is one of the most useful things chemists can take advantage of to perturb a reversible reaction and force it to go more in one direction or the other and potentially arrive at a new equilibrium position. This is named after Henri Louis Le Chatelier, who is a French chemist. And as an example, I'm going to look at the Haber synthesis of ammonia, a very important reaction for the fertilizer industry, and just how we make ammonia by fixating nitrogen and combining it with hydrogen gas. First, let me show you the most common stresses that chemists can apply to reactions and how it affects the direction of an equilibrium. Then we'll look at a video of an example with this process applied to a specific reaction, and close up with how this relates to some other things we talked about related to equilibria. So let's say I'm doing this reaction. I'm making ammonia by combining nitrogen and hydrogen, and I want to force it to go in one direction more than the other. It's reversible, but what can I do in the laboratory to stress this reaction and force it to go more one way? The first thing you could do is simply change the amount of a reactant or product. Let's say I increase the reactant concentration. Well, this reaction is going to respond by offsetting that stress and going away from the reactant side. If we add more reactant, whether it's nitrogen or hydrogen, it will offset that by shifting forward. It will go to the right to offset that. Likewise, if I added more product, that would reverse this and make it go backwards. That also means if I remove something, it will offset that by trying to replenish it, and that's one of the most useful things we can do in the lab. I did this a lot in graduate school when you're doing a reversible reaction and you're forming something, and if you remove it as it's being formed, it forces the equilibrium to shift more in the forward direction. There's different ways to do that depending on what the molecule is that you're making. The second thing that you could think about doing might be changing the temperature. Let's say I heated this reaction up, just heat it up. We know that that makes everything go faster. How does that affect the equilibrium? Well, it depends on if it's an exothermic reaction or an endothermic reaction. This one happens to be exothermic. And if you increase the temperature, the way to remember this is think of heat as a product in this case. So it would offset that additional heat by going in the endothermic direction in this case, which is backwards. So this would go to the left as a result. This actually also changes the numerical value of K. Remember, K only changes with temperature and with what the reaction is. If you change the reaction completely, then the K value is different. But otherwise, K is a constant. But because we're changing temperature, that does change the value of K. It turns out that when you heat up an exothermic reaction, K gets smaller. We'll talk about why that is later on in the course, but for now I'm just going to put that there and you can remember that that's the case. That means the opposite is true for an endothermic reaction. If this was an endothermic reaction and we had heat as a reactant, if I heated it up, that would be analogous to adding heat, and it would offset that by going to the right. And as a result, K will increase in numerical value. Tiny little footnote here, you don't need to know this, but it has to do with this Arrhenius relationship. That's why the numerical value of K changes. That's because the activation energy for a reversible reaction is different for the endothermic direction as opposed to the exothermic direction, and the rate constant of one direction over the other changes differently as you heat them up. Everything gets faster as you heat it up, as you increase the temperature, but the rate constants don't change by the same proportion, so you end up increasing the endothermic direction more when you heat up a reaction. That's a little bit more than one needs to know for the AP exam, but that's a little bit about why this actually changes the value of K, and we'll see that later on in the course as well. Something else you can do to a reaction, particularly for gas phase reactions, is you can change the volume of the container that you're using for this reaction. Let's say I'm just doing this in some reaction vessel of a fixed volume. Let's shrink it, make it smaller. What that does, think about Boyle's law, is it increases the partial pressure of every single thing in the reaction. All of them, the reactants and the products, all increase the partial pressure if you shrink the space. And as a result, the reaction in this case will shift to the right. That's because it wants to go to the side of the reaction with fewer gas molecules, which I can figure out just by looking at the coefficients of everything that has a gas. So there are 4 gaseous reactants, but only 2 gaseous products. 4 moles of gas become 2 moles of gas in this case. And a smaller volume is going to make it so that I go to the right-hand side in this reaction. This is where you only look at gases, and you can easily change that by changing the volume. What about if I add some other gaseous species that's actually not a reactant or a product, just some inert gas, like I'll throw in some helium into this reaction vessel. Now, as long as the volume is fixed, that actually means the partial pressures of the other gases don't change. Remember, gases are selfish. They pretend that they are the only one that's there. They occupy the entire space in which they exist, even if there's another gas that's present. And if it's an inert gas, that actually means there's no change in the equilibrium, and that's because the partial pressures have not changed. The total pressure will have increased, but that won't affect the equilibrium because the partial pressures of the reactants and the products are the same. What about if we add a catalyst? Last thing to mention here that you might see asked about is what happens if you add a catalyst to this? In our kinetics unit, we saw that catalysts increase the rate of a reaction by lowering the activation energy. That means you'll speed up both directions of a reversible reaction, and you also have no change in the final point of equilibrium. You'll simply get there faster. It'll equilibrate faster because both directions of the reversible reaction will have sped up as a result of adding a catalyst. Okay, so those are the most common stresses that we see that we can apply in the laboratory to a reversible reaction to manipulate it. And the first 4 certainly show you changes that you can affect. The other 2 don't have an effect, but they're pretty commonly asked about, so that's why I wanted to make sure I add those to your list. Now let's take a look at a different reaction and see this in action. Here is a cobalt complex, a cobalt chloride complex ion. It happens to be blue in an organic solvent, and then if you mix it with water and make it aqueous, the chlorides actually leave and you get this hexa-aqua cobalt complex that's a completely different color. It's a pale pink. So we can monitor which side of the equilibrium, the reactants or the products, this reaction predominates on just by looking at the color of the reaction. I'm going to show you a quick video that illustrates this. We'll try to predict it as we go, and then we'll recap what we see after we watch the video. So here's the video. There's the cobalt complex initially, several test tubes of it. Initially it's blue and it's just in ethanol, not in water. Now when we add a little bit of water there, it immediately turns into that pink color, the hexa-aqua. That's because we're adding a reactant, so it shifts towards the product side. Now let's change the temperature. Here's 2 side by side, a blue one and a pink one. You'll notice from the reaction at the top, this is exothermic. So if we're adding heat, it's kind of like adding a product. That means it'll shift to the left. We should see pink becoming blue, and blue stays blue. In fact, that's exactly what we see. Now let's see what's next. Now we're going to remove heat. I think that's a cold water bath. If we remove heat, that's like removing a product from the reaction, so it should go more forward, which means blue should become pink, and pink should stay pink, and indeed that's what we see. And then there's a bottle of HCl. Hydrochloric acid, remember that's a strong acid, totally dissociates, so this is a source of chloride ion. So I'm imagining adding chloride, that's a product, which means the reaction should shift to the left. So we should have pink becoming blue and blue staying blue. And then I guess I made one turn back into pink by adding water there. And then lastly, there's solid calcium chloride. I don't see calcium anywhere in this reaction, but it is a source of chloride. And chloride, again, is a product, so this is the same as adding HCl. That will turn it from pink to blue, and blue stays blue. So let's just recap this back on our notes here and write what we saw. Initially, we had just the blue cobalt complex. We added some water. That's a reactant that will force it to go forward, which means it changed into pink. Then we added heat. This is an exothermic reaction. So if I add heat, that's like adding a product. That means it's going to shift to the left, and we're going to turn it back to blue. Doing the opposite turns it back to pink. Removing heat would make this reaction go forward, and you'd make more of the pink complex. And then lastly, adding calcium chloride is essentially a source of chloride ion. That's a product that would make it shift to the left, and you would get more of the blue complex as a result. Okay, so now let's wrap up by looking at this a little more quantitatively and relating it to some of the things we said earlier in this unit. Here's the same reaction we talked about in the beginning, the synthesis of ammonia from nitrogen and hydrogen, that's N2 plus 3H2s, makes 2 NH3s. And let's say I know exactly what my concentrations are at a point of equilibrium, and then I perturb it by increasing the concentration of one of them. What's K? And what's Q as a result. So first of all, a review of how you write the equilibrium constant. The equilibrium constant is the products over the reactants, each raised to their coefficient. So K, in this case, is going to be the ratio of the ammonia concentration squared divided by the nitrogen concentration times the hydrogen concentration cubed. I'm not going to write that out in the expression, I'm just going to plug in the numbers. So the ammonia concentration, they tell me, is 0.2. Don't forget to square it because of the coefficient of 2. And then divided by the nitrogen concentration, that's 0.4. And then divided by the hydrogen concentration, which is 1. Don't forget to cube it because of the coefficient of 3. Without a calculator, we should be able to get those numbers. That becomes 0.04 divided by 0.4. That's just a tenth. So K for this reaction at some temperature, I suppose, is 0.1. Not particularly small, not particularly large, actually. So substantial amounts of both species, reactants and products, all three species really, at whatever temperature we're talking about. Now we change it. We change it so that we change the nitrogen concentration to be 0.8. It used to be 0.4. We're going to double that. What's that going to do to this reaction? And let's compare that with Q. Remember, Q, the reaction quotient, has the same expression as the equilibrium constant. It's just not necessarily at equilibrium. And that's true. Once we change the amount of one of these things, temporarily, it's not at equilibrium. It will respond, but temporarily it's not there. So initially, our numerator is the same. It's 0.2 squared, because the ammonia is still 0.2, but the denominator is different. Now my nitrogen concentration is 0.8 raised to the first power, and my hydrogen is still 1.0, also cubed. You could do that without a calculator. That's 0.04 divided by 0.8, that's 0.05. So remember when we first introduced equilibrium a few lessons ago, we were able to predict which way a reaction is going by comparing Q and K. And in this case, K is greater than Q. That means the reaction will shift more to the forward direction. There is not enough numerator, there's not enough product for this to be at equilibrium, so we're going to get more forward reaction. That's exactly what we just said with the Chatelier's principle. This is the same thing. Comparing Q and K is doing Le Chatelier's principle, applying Le Chatelier's principle. The reaction shifts forward. There's a good little tip that I'll put here as a footnote that I find very useful when you're comparing K and Q and predicting or remembering which way the reaction goes. As long as you write K first and you compare it with Q, the inequality greater than and less than looks like an arrowhead. So if K is greater than Q, it looks like a forward arrow, and indeed the reaction goes forward when that's true. And then the opposite is true. If K is less than Q, it looks like the arrowhead pointing backwards, and it goes backwards. You have to write K first in order for that to work, but when you do, you don't even have to remember the why. You can just remember the what in this case. Lastly, there's a graph here that lets us just visualize what's going on in terms of equilibria. So let's plot these three species on a graph and look at how they change. We've got nitrogen, hydrogen, and ammonia. I'll make them three different colors and just arbitrarily put them somewhere on this y-axis. The ammonia is the lowest concentration at 0.2. Then we have the nitrogen at about 0.4, and the hydrogen way up there at 1.0, not to scale, just roughly relative to each other. Then we change the nitrogen concentration. We spike the nitrogen concentration up to 0.8. So we initially charge up a lot of nitrogen. We just said that means the reaction is going to go more forward. Yep, because Le Chatelier's principle says that it will offset the stress, in this case of adding a reactant. That means we're going to get the nitrogen and the hydrogen are going to react. So as soon as we add that, we're going to decrease those concentrations, and we're going to get more product. So here's our initial equilibrium state. What will it look like after that change? Well, hydrogen's going to react, and it's going to decrease in concentration. Then nitrogen is going to react and also decrease. Notice that the decrease actually isn't to the same rate as the previous one. There are 3 hydrogens reacting for every 1 nitrogen, so I intentionally have this slope of hydrogen steeper than this decrease of nitrogen. And then the ammonia is going to increase in concentration. We're going to form more ammonia. But in the end, we hit a new plateau and we reach a new equilibrium state where the concentrations no longer change with time. And as long as temperature is the same, you have the same numerical value of K. Lots of different combinations can give you that one numerical value of K back to 0.1 as a result. Okay, so Le Chatelier's principle is all about stressing reversible processes to force a reversible reaction to go more in one direction or the other. We have various ways of manipulating this, changing temperature, changing volume for gas phase species, or just changing the amount of what we call a reactant or product to get it to shift in that direction. Thanks for watching, chemists.